Welcome back, my dear learners. I'm still teacher Namugongo Isaac. We were looking at waves, and in our previous session, we ended with the relationship between period and frequency. So we concluded by getting period is the same as 1 divided by the frequency. That is what we concluded with. We looked at the SI unit of period, and we also looked at the SI unit of frequency. Period can be measured in seconds, and frequency is measured in hertz. So we are going to continue and look at the relationship between what we term as V, the velocity. We shall also look at the relationship between V and the wavelength lambda. So we shall have wavelength lambda and the frequency. The wavelength lambda and the frequency. So we are going to have, if a wave is traveling from one point to another and it is covering a number of cycles in a given time frame, say time is t, then we are going to have that as our frequency. But remember, we can define velocity. We can define velocity. Velocity, we can define it as the distance this wave is going to cover in a given time. Or someone can still call it the displacement of the particles from one point to another in a given time. So that will be our velocity. So this we can then go ahead to write it as the distance covered divided by the time taken. The distance covered divided by the time taken. So this is the velocity. Now we want to bring in the wavelength and the frequency. But how? How shall we bring it in? We shall bring it in by looking at the distance. For a wave to move from one point to another, it will take it n number of cycles. It will take it a number of cycles. And these cycles are going to be repeated for every given period and for a given distance in terms of wavelength. So the total distance will be the wavelength times the number of cycles. So this means we are going to have, therefore, the distance being the number of cycles times the wavelength divided by our time t. Remember, in the previous scenario, we said that frequency is the number of complete oscillations per given second. So we shall come and say that f is equal to number of oscillations per given cycle. Now we are going to rewrite this, and we shall form n divided by t times lambda. So I've just categorized n divided by t and multiplied with lambda. So where we have n divided by t, we shall substitute with f, and we shall have f lambda. And this is what we are calling our velocity. So this expression here is what we are calling the relationship between the velocity, wavelength, and frequency. And it is what we call the wave equation. So this is the equation which describes our wave, and we can use it to calculate numbers. Alternatively, we can have that when a wave covers a distance lambda, when a wave covers a distance lambda in a given time, remember we said that for a wave to make a complete oscillation, because we are moving from, for example, here, and this will be a complete oscillation, it takes its period. And period, we say this is the time taken for a complete oscillation. So if we are going to do this, then we are going to have that our value is going to be the distance, the time taken. So it will be V, alternatively, is equal to the distance times the time taken. This time is 1 out of t, which we call the period, times the distance, which is lambda. Now, when you convert, because we concluded also by saying that t is equal to 1 out of f, similarly, if we made f the subject by cross multiplying here, you will find that we get f is equal to 1 out of t. So this takes us down. Wherever we have 1 out of t, we can substitute with f. So therefore, the wave equation therefore comes as this. So we can either get it from the definition of the velocity or from the combination of the definition of frequency and the lambda. So meaning for every given one oscillation, it takes 1 out of the period, and then we shall multiply it with the wavelength. So in this way you can come up with the equations. We looked at classifications of waves where we say we have mechanical and electromagnetic, but we have types of waves. So the different types of waves we have transverse and progressive waves and stationary waves. So we have progressive and stationary waves. What are these? So we start by looking at progressive waves. Progressive waves are waves which are transferred or which move from its source through a given medium and spreads out continuously. In other words, one can say, if you have a source, the wave will be generated here, and its motion in that direction will continue. So it will not cease. So it's, in other words, it is progressive from point to point. Under this type, we have longitudinal. Under this type of wave, you can see the example. We have longitudinal waves, and we also have what we call the transverse wave. So those are the two examples under progressive waves. So we move on to look at what each of these is. A transverse wave. A transverse wave is a wave in which the propagation of the wave is perpendicular to the direction of the wave in which it is traveling. What do we mean? We have this wave here, and for perpendicular lines we have to form 90 degrees. So this wave, for example, if we took particles vibrating where we have the crests, they are going to be perpendicular to the direction in which the wave is moving. So these take us to the examples of waves on a rock. waves formed by water, and even some waves formed by the strings when you oscillate them up and down. Graphical representation of a transverse wave. I've already shown you, so meaning these particles will vibrate up and down, up and down, but they vibrate perpendicular to the direction of propagation. Then we come to the longitudinal waves. What are these waves? These are waves that propagate parallel to the direction of the wave. So in this case, if you have the wave propagating in this direction, these waves vibrate parallel. So in other words, they are going to move with what we call compressions and rarefactions. They will not vibrate up and down. So they vibrate parallel to the wave. Examples of longitudinal waves, we have sound waves in a closed pipe. We also have waves produced by strings when strings are pulled. Strings pulled. So you pull a string, it will generate a parallel oscillation of this form. So we form a wave. We also move on to look at the graphical representation of a longitudinal wave. So if I am to sketch and I have my string fixed at one point, when I fix it there, I'll pull and it will form big gaps, and at some point it will form small gaps. Big gaps, small gaps. These here are what we are calling the rarefactions. And these are what we are calling the compressions. So I'm denoting them by capital R and capital C. So the region where we have wide gaps between the wave, those are rarefactions. They are spacely organized. Whereas where we have narrow gaps, these are what we call compressions in these waves. So if you're to define them, you can simply say this is a region in a longitudinal wave for a compression. This is a region in a longitudinal wave where the wave particles are tightly bound, or they are very close to one another. And when you look at rarefactions, still you will say this is a region in a longitudinal wave where the wave particles are widely spaced or are further apart from each other. Because we have different forms of waves, in this case we can also be asked to define the wavelength. And the wavelength of a longitudinal wave is the distance between two successive rarefactions or compressions. And what do we mean? So if this is a rarefaction and this is the next rarefaction here, then this is going to be lambda. We can also have from here up to another. So this is from a rarefaction to a rarefaction, we get lambda. Successive, meaning following each other. Then this is from a compression to a compression, following each other. We also form lambda, the wavelength. So distance between two successive compressions or rarefactions in a longitudinal wave, we can call that the wavelength. A question. Someone can come and set for you a question and say, give the differences between longitudinal waves and give the difference between longitudinal and transverse waves. Longitudinal waves have their own characteristics, whereas transverse waves also have their characteristics. So this question is as simple as what we've gone through. What you do, the easiest format is to draw a table. When you draw a table, then you can easily differentiate them. So we have longitudinal waves, and you can also have transverse waves. So we are going to differentiate between these two. What did we look at? What did we look at? We have one. Under longitudinal, we've seen that they have rarefactions and compressions. Whereas in transverse, we have crests and troughs. So that is the first difference. So you can write it, have rarefactions and compressions. So have rarefactions, whereas this side we are going to say have rarefactions and compressions. This side we shall say have crests and troughs. That is in the futures. We can also differentiate them by the definition. A transverse wave is, it vibrates perpendicularly to the direction of propagation. This side we can write and say that this vibrates, I beg your pardon there. So this is supposed to be on the side of transverse. This vibrates perpendicularly to the direction of propagation. This vibrates parallel to the direction of propagation. Lastly, longitudinal waves cannot be polarized. Whereas transverse waves can be polarized. So this is how you can attempt this question in case it came and they needed the differences. So we can move on and look at some examples where we have questions and we can try them out. On the screen you're going to be provided with a question and we can try out the questions that follow. We have a diagram of a wave traveling. It has point X and point M. They've given us the distance from here to here as 0.m. 8 meters. And we also have this as our rest position. Down they have given us that we have from one point to another. This wave, the total distance is 8 meters. So we have questions that follow after this diagram. We have questions that follow after this diagram. Name any 2 points on the wave which are in phase. So we had Y here and Z. Which points are in phase? Points in phase for Roman number 1, part A, we have Y and Z. They are at the same point of rest at a different given location. So they are in phase. If we had another point here and another point here, these will also be in phase. So that's what we mean. Roman number 2, the points labeled M and X. Name the points labeled M and X. In a transverse wave, we saw that X is the crest and M is the trough. X is the crest and M is the trough. If we are to continue, another question says determine the amplitude of the wave. What did we say amplitude is? This is the greatest or maximum displacement of the wave particle from the rest position. So our rest position is 0. The rest position is 0. And we are seeing that we can vibrate, or this wave vibrates from the rest position to X, and it can also vibrate from the rest position to M. But we only need A. That is what I'm denoting. Our A is the amplitude. So you can either get it from above the rest position or from below the rest position. This total distance is given as 8. So part B, Roman number 1 will be given as the amplitude is going to be the 0.8 divided by 2. Why are we dividing by 2? It is because 0.8 is the total distance from the crest to the trough. But the amplitude is from the crest to the rest position and as well from the rest position to the trough. So take note of that. So we shall divide 0.8 by 2. This gives us 0.4 meters, and that is our amplitude. The next question says, if this wave is moving at a speed of 80, if this wave is moving at a speed of 80 meters per second, a speed of 80 meters per second, how or determine the frequency? We recall that we said frequency can be got from the wave equation. Our wave equation was V is equal to frequency times the wavelength. What do we have? Take note, always look for the given things in the question. Do we have V? Do we have F? And what do they need? So, we shall first start with what is given. V is given. V is the velocity. So, V is equal to 80 meters per second. F Is it given? No, we don't know it, so we shall say f is equal to, that is what we are looking for, question mark. Then lastly, lambda. Is lambda given? Lambda is not given, but when we look at our diagram, we say that wavelength is for a complete oscillation. These are two complete oscillations. From here up to where I'm going to label, you move. This is one oscillation, and this is the first. Then move again, second complete oscillation. So for each complete oscillation, we said we can take that as the wavelength. Now here comes, they have given us the total distance of two complete oscillations. So we shall get lambda by dividing 8 by 2, which gives us 4 meters for one wavelength. So we come back and substitute in our formula. What do we have? We have that V is equal to 80. We have F, which is not given, and it is what we require, times lambda, which is 4. So we need F. Mathematically, we shall make F the subject. How? We shall divide through by 4 on both sides. So V, which is 80, divided by 4 will equal to F times 4 divided by 4. 4 and 4 this side will cancel. 80 divided by 4, we get 20. So F is equal to 20. Recall our units. The unit of frequency was a hertz, which I said should be a capital H, and the Z, to show that it is a small letter, it is halfway the Z. So this is how you can try out a number in that form. Last but not least, I'm going to write for you a question, and we shall try it out. We shall try it out. Shall try it out. A wave is moving with a speed of 5 meters per second. A wave is moving at a speed of 5 meters per second and has a frequency of 10 hertz. Full stop. Calculate the wave length of the wave. Calculate the wavelength of the wave. So we shall go on to say, from our wave equation, we have that V is equal to F times lambda. We go on to substitute. I've said always write down what is given. What do we have? Read through the question. A wave is moving at a speed. So we take the speed as our velocity. So V is equal to 5 meters per second. And has a frequency of 10 hertz. So they have also given us frequency of 10 hertz. What do they want? They want the wavelength. So we want lambda, put our question marks because we don't know it. So we are going to pick these values and substitute them in the formula. So we shall have 5 is equal to F, which is 10 times the wavelength. How do we make the wavelength the subject? We divide through both sides by 10. So we shall have 5 divided by 10 is also the same as 10 times lambda divided by 10. So 10 here and 10 here will cancel. You can use the blue to show you what has cancelled. And we shall end up having that lambda is equal to 5 divided by 10, we get 0.5 meters. 0.5 meters. So this is how you can attempt a question if it came in that order. I thank you very much for attending this session of waves. Please stay tuned because more is to come. Subscribe, share the video so that all may learn. Thank you very much.